Hi, today we're looking at shortcut learning in deep neural networks by a number of authors from the University of Tübingen, the Max Planck Research Center, and the University of Toronto. So I'm not going to read all of them, but all of them are either joint first authors or joint senior authors. What is this? It's just a team of people who did this work together. This whole, I have a star, I don't have a star, I have a cross, whatever. Okay, sorry, bit of a rant. All right, so this paper discusses what they call shortcut learning, and they don't propose something new here. They discuss this phenomenon, and they try to link several things together under the name of shortcut learning, which they claim is a problem in current deep learning, and they discuss why it happens and what can be done about it. And I just want to jump into this example real quick, right? So in this case, you can see you have a training set of images, and the training set is these 4 images here, along with these labels, and also these 4 images along with these labels, right? So you can think you can train a machine learning model. Let's say you have a bunch of those, and then you're going to test them on the IID test set, right? On this test set. And what you'll find is that if you let a human do this task, right, the human would give this an A, this an A, this a B, and this a B, which is what you can think of is probably what a human would do is like, these are the stars and these are the moons, right? And the human would see the stars and the humans would see the moons. And if you do this by the neural network, also you'd get the labels A, B, and B. And now you go about this out of distribution test set, and we'll go over it, why that is out of distribution in a second. Again, you'll see that the human will classify this as the A's because it has the stars, and these as B's. But the neural network will classify these as B's and these as A's. So I'm not saying this is what's going to happen every time, but imagine that happens. And this is a conceivable situation. And you can think of what happens here. So you see in the training set, all of the stars were either on the bottom left, right, or in the top right of the image. Where whereas the moons were either in the bottom right or the top left, right? You see that, so the neural network might have learned that this is moon, and this is moon, and this is star, and this is star. And then if it applies that rule to this new test set, right, then you can see that it'll classify these as moons and these as stars, which is incorrect, right? So this might happen, for example, if the person that wrote the generator for the data set, for some reason, it produced only data here that had this property of the bottom left, top right being a star and otherwise being a moon. So what generally happens if we do machine learning test set is we collect a data set, a big data set, but we collect it in a single pass, right? So this is our data set. And what we'll do then is we'll split it, right, into a fairly large train and maybe a bit of a smaller test set, right? But it's important that we first collect the data, and then second, we randomly split it. Now, this out of distribution test set, what that might be is, that might be a second person, right? So this was done in a first step, but then later, right, a person collects another bunch of data. So this is data 2, and they think it should be the same as this data, but then you apply the classifier that you learned in train and test, you apply that here, right? So what is different in this case is the data collection process that happens beforehand, right? So somewhere here is the real world. I'm going to draw the real world. It's a globe. This is the real world, and you draw data sets from the real world. And you draw this data set first, and then you split it in train and test, and then you draw this data set second. So the second data set has a fundamentally is a different sample of data than this data, whereas these train and test, you can think of them, they are closer together than these two data sets are here. I think that's kind of intuitive. So what we usually do is we train here, and then we evaluate on the test set, right? But the train and test set, they're just like randomly split versions of the same data set, and that means that if there is some kind of bias in the training set, it's probably also in the test set, like we saw here with the moons, right? So this training set is this test set is this, and both have this moon star property because that was introduced. So this pattern here, by accident in this case, was introduced when the data was produced, right? Whereas the OOD test set now is maybe a second person writing their own generator that doesn't have this property, and then that will lead to this data. And of course, since we train on this training data, evaluate on IID data, this is now the IID assumption, and evaluate on the IID test data, we're going to do fairly well with our, crooked decision rule because it has the same bias. But then once we evaluate on the out of distribution data, then we will fail, right? Because now this doesn't have this bias in it, right? This is not here. So shortcut learning refers to the phenomenon that there might be features in the training set that the model starts to learn, such that it learns something else that we want it to learn, right? We want it to learn the shape here, but it learns something else. It learns the position. And usually these things will not be recognized by generalizing to this test set, right? Because the test set, being an IID split from the same training set, will have these same biases. And therefore, they will only become apparent once we do out-of-distribution generalization evaluation. So this is shortcut learning. And this paper goes into the origins and kind of descriptions of this. And while I think this is a good approach and paper, and it says many correct things, I think the framing is a bit off at times. And we'll go through it. So first of all, they give some examples in biological neural networks. So they have this one example where they have a rat, and the rat learned to navigate a complex maze, right? Based on color differences of the walls. And this was surprising because rats don't really have color vision, or it was kind of known that rats don't have super good color vision, so it was very surprising. And then they discovered that the rats did actually not use the visual system at all. They simply discriminated the colors by the odor of the color paint, right? So if you painted the wall red or blue, that smelled differently, and the rats could smell it. Once they controlled for the smell, the remarkable color discrimination ability disappeared, right? So the second example they give here is, so Alice loves history, and Alice had spent weeks immersing herself in the world of Hannibal and his exploits in the Roman Empire, and now the exam questions are just like, how many elephants did Hannibal employ in his army? So the exam questions are multiple choice, not focus on understanding, and Bob had just learned it by heart and is now doing much better than Alice, who has actually understood the topic, right? So they give this as examples of shortcut learning, where the model learns something that we don't intend it to do, right? All right, and I think this is the crucial point, right? The model learns something that we don't intend it to do, right? So here, and this seems this might be pretty clear to when you observe it, but what do we want? We want shape. And the model learns something else, right? Just something else. And the crucial part here, and I think this paper isn't putting as much emphasis as it deserves, is the two words we and want. So basically my answer to this is, first of all, the word want. We want shape. And my answer, my comment to this is, you can't formulate that. You can't formulate it. This is very crucial, and I think the paper almost ignores this point. You cannot formulate what it means to classify things by shape, and this seems so oblivious to us because we're so used to it as humans, right? We're just like, oh, just use the shape, right? This is the shape, right? But you cannot program a computer to do this. That's why we use deep learning in the first place, right? Because we have no freaking idea how to program an algorithm that extracts the shape of something. It might be possible for like a star and a moon, but not for a cat or a car or anything, right? So you cannot formulate your objective. That's the problem, right? And it's easy to then say, oh, the model doesn't do what we want it to do. It's like you can't even formulate what you want it to do in a precise way. So basically all you're saying here, what you're saying here is, I'll train a shape classifier, right? Once you've gone through this process of training and evaluating, you say, now I have a shape classifier. Right? Say you hadn't done this OOD evaluation. You've gone through this, and you now proclaim, I have trained a shape classifier. No. You have trained something that, given the entire process of how you create your data, can classify these two images, right? So here is your generator. This is your little program that you wrote to produce these images. And your generator assigns either the star, right, at random, it produces these things, the star or the moon. It does these two things, and then it creates the image from it, and that will give you your data set, right? What you have trained is not a shape classifier. What you have trained is a classifier that can distinguish data that comes from this data generation process, right? The entire notion of calling it a shape classifier is because you as a human have thought of shape when you programmed this generator, right? When you collected the data set, that's what you thought of. But this isn't the case. You can't call it a shape classifier just because you, like, this is what your intent was. You have a classifier that classifies images from this particular data generation process. And you can't actually formulate a shape classifier. Right, okay. The second word is we. We. Sorry. We. Humans. Right? We want a shape classifier. Now, I've said this before, and this very much refers back to for example, the paper about the contrast sets in NLP and so on. Humans have grounded knowledge, right? Humans have grounding. This is very important here. Grounding means that the humans live in a world of physics and culture, physics and culture, and the need for food, biology. Humans live in this world, and this generated our brain, right? So what that means is that humans live in a world of objects and of people and of being eaten, right? Being eaten or needing to eat food, right? Humans grew up and live in this world. Your brain was literally structured according to these things. And thus, we understand everything with an eye to this grounded knowledge of reality, where there is such a thing as objects. Now, if you have ImageNet and you train a classifier for objects, right? This is what I find so crazy, right? And you collect this thing and there's a car and you say, that's a car, right? You know this is a car because there is an object of a car. But the neural network does not have a bias for object. The neural network simply sees these pixels. Same here. What you will do immediately here is you'll recognize the object of the star, right? You will transform this into a 3D scene, right? Into a 3D cube where you are here watching in 3D space, and there is this star object somewhere here, right? And then you understand that the star could move around and it would still be the same star, but that's because you have the inherent bias of there being objects. And shape, for example, the word shape is nothing more than a property of an object, and the neural networks simply do not have a inherent bias for objects, right? Or people, or intent, or what it means to eat, right? This becomes super obvious if you ever try to solve, for example, a jigsaw puzzle, like these things here. I'm terrible at this. If you solve this on its head, right? Say this has like a face on it, and you try to solve it like this, and you try to solve it on its head. Like, try it. It's the same task. You simply need to match the border shapes, right? And you need to make sure that the lines are continuous of the picture. It becomes so much harder just because you have this brain. And so that is my entire criticism, and it will pull through this entire paper. And we'll go through it for now relatively quickly because we've already touched on it. Keep in mind, this is my commentary on it. This is not superior knowledge or something. That's just me. All right. So what they do is they have this taxonomy of decision rules that they point out. What they're saying is, okay, there's a set of all possible decision rules, right? And this is the outer set here. All possible decision rules that one could think of to discriminate data. And let's say we'll talk about images here, right? To discriminate images. Most of them will just be crap, and these will be using these uninformative features, what they say. But then there are some decision rules that perform well on training data, right? This is this big circle here, right? So that there are some decision rules that perform well on the training set, and they call these overfitting features. So these are all the features that perform well on the training set, only on the training set, sorry, the overfitting features. But to me, it's a bit unclear. I think they only call this band the overfitting features, but they call the entire circle the all possible training solutions. Any case, so there are decision rules that perform well on the training set, but some of them are overfitting, as you know that problem, right? Then the next circle, inside of that, are all decision rules that perform well on the training set and the IID test set. And this would be our location classifier from before, would fall into this category, right? And now, these are still a much larger set, as you see here, as this inside set of the intended solution. Performs well on training set, IID, and all relevant out-of-distribution test sets, right? And they draw this in here. The out-of-distribution test sets are subsets of the IID test set, or the solutions that work on the OOD test sets are subsets of the solutions that work well on the IID test sets. Right? I don't have a problem with this characterization of decision rules, right? Here specifically, these are decision rules. What I have a problem of characterization with is the fact that you cannot specify what the intended solution is. You cannot. And therefore, this diagram, I think, is misleading because you have ultimately you have no idea where this dot is, right? You can't specify it beforehand. You can't even specify the rules how you get there. All you can do is give better data. And they kind of advocate for this here with these OOD test sets, but again, I think when they say all relevant out-of-distribution test sets, I'm a bit wary because they suggest this as one of the measures to assess whether or not a model has learned. These shortcut rules is to measure its performance on out-of-distribution test sets, and this is very much like the contrast sets in the NLP, but I think actually this is a pretty bad solution in most cases. And let me explain why. So if we go back to here, right, what we saw is that these discrepancy, it comes about because here, from the real world, we produce the data in a very specific form, right? And then this other out-of-distribution test set is produced in a slightly different form, right? Now, what you can think of this is, if you look at your cost function that you train, right? What you usually say is my cost function is some sort of a loss for my data points and my labels. Right? But this is often left out. I mean, you write it in your introductory classes. What is important is that this is an expected loss that you're minimizing here over a data distribution, right? Over X and Y, sampled from a particular data distribution. Now, when you talk about this, this out-of-distribution classifiers, what you'll have is you'll have a slightly different data distribution, D prime, right? So, but if you simply have one out of distribution thing, think of this as the contrast set, right? If you haven't seen the video about contrast sets, it's basically a handcrafted out of distribution test set, right? My problem with this, it's just one. It's one. It's a single one. And I think even if you try 10 of them, 10 of those sets, you won't even get close to a true measure. Because, so the cool thing about an IID test set is at least it is precisely the same distribution, right? So it kind of gives you an unbiased number that for this particular data generation pipeline, you get this number. If you evaluate on an out-of-distribution test set, you now have two effects. You first have this generalization effect, and you have the effect of having produced this in a different fashion here. But you only have one of them. What you would like to do is what you would like to assess is your loss of x and y in expectation, with x and y coming from data in expectation, a different color, in expectation, with your data distribution coming from all possible data distributions in the real world, right? That's what you would like to say, to do. Now, if you only have a single contrast set, it is akin, you can think of what if, like how well of a machine learning engineer would I be if my test set here only had one sample, right? So I give you a train and a test set, and I'm saying your performance will be, I make a Kaggle challenge, and I say your performance will be evaluated on this one single sample test set, right? That's basically what you're doing if you have a single OOD test set, is you're saying, I'm going to give you one out of distribution data set that I have biased in one particular way, right? And we'll measure how well you capture our intent, right? Our shape classifier intent. We'll measure how well you capture that using this one single out of distribution thing. I think what that will do is, right, you say, I want to approximate this by a sum of I equals 1 to 1. That will just pump the variance beyond beyond any reasonable meaning that the outcoming number will be able to give you. What you'd have to do is you'd have to have this entire process and sample, train, and test sets according to this data, or at least test sets according to this data distribution, this underlying data distribution, which you have no clue what it is, because if you could specify this directly, you could get the solution for free, right? If you could specify the underlying mechanism, you would already know the solution. You wouldn't need machine learning. So I think the model puts like way too little emphasis. Sorry, the paper puts a bit too little emphasis. Suffice to say, with their taxonomy, they can say if you use, for example, only the overfitting features, right, then you will do well on the training set, but not on the IID and OOD test sets. If you use the intended features, again, intended, no one knows what that is, no one can specify it, you'll do well on all the OOD test sets. If you use the shortcut features, you will do well on the training and IID test set, but not on the OOD test. This is valid, right? I'm not discrediting this paper here, and they do allude to a lot of the things I'm saying, but not all. And I don't think they frame it correctly. So they ask, shortcuts, where do they come from? And they say a lot of the things that I've been saying here. But for example, they ask, what makes a cow a cow? And they give this example here where they say a familiar background can be as important for recognition to deep neural networks, where the deep neural networks will misclassify this picture because they're used to seeing a cow in grass. Now consider this in our framework, right? If, let's say this is an ImageNet classifier. ImageNet is not an object classifier. It is not, right? That's what we say. That's our intent. But what it is a classifier. If you go through the pipeline, how do you generate the data? ImageNet is a classifier of naturally taken images, right? With a certain camera cropped, center cropped to a particular object, labeled by human raters, filtered in some capacity, right, from Flickr. And for that particular data set, we train a classifier. It is not an object classifier. It is a classifier for that. And it has no clue of objects. So, in fact, and also what you have to see is that the output isn't, even if the output is shape, it isn't shape. It is actually probability of shape, right? Or probability of object, or probability of something, right? And it is completely conceivable, right, that if it's not grass in the background, it's probably not as much a cow. Now, I see the problem here. This is clearly a cow, and this is actually a conceivable natural image. But imagine a picture of the cow. Oops, what happened here? On the moon, right? This is the moon. And here's the cow. Cow. Moo. This is terrible. Horns. Tail. A cow on the moon. Like, who can fault the neural network? And I would say that's not a cow either, because in terms of the data generation process, if you ask me, please classify this as a natural image that has been taken, blah, 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 right? I'm going to say there's no way there's a cow on the moon. So I don't know what this is, but it is very improbable that this is a cow, right? Because all the training examples I've seen, cow on grass. So, yeah, so I mean, they do actually allude to this, right? They call this data set biases and so on, but I'm pretty sure that the interpretation is just a bit off, where they say the point of this is like, it's you know, we want an object classifier, but this we want. The second I find even more kind of strange is they say shortcuts from discriminative learning, and they allude to this picture here, and they ask, what makes a cat a cat? And they basically, their argument is that the neural networks, they don't understand things, they just discriminate, right? They have these 1,000 classes and the output layer, this is the neural network, and they just need to discriminate, so they just need to learn what is different from one class to the other class. They will often rely on features such as texture, like here. So they rely on the texture, and they classify this as an elephant, right? So they say, what makes a cat a cat? To standard DNNs, the example image on the left clearly shows an elephant, not a cat. And again, I agree. If you tell me this is data from naturally taken images with standard cameras, right? Then I will have two possibilities. I will say, is this a cat? There's no way that if you take anywhere in the universe a picture with a phone camera of anything, of a cat, it will look like this. No way. This is just not possible, right? However, is it possible that there is an elephant that, as a skin fold pattern by random chance, elephant, big ears, raw trunk, as a skin fold pattern, looks like a cat, looks like the shape of a cat? Yes, that's possible. So if you ask me, according to the data generation process, this is way more likely to be an elephant than a cat, right? And the paper here makes it seem like it is so obvious that this is a cat, but what do the standard stupid DNNs think? It's an elephant, not a cat. And the DNN, it's just looking at object texture and other local structures and not at shape, right? What we want it to do. And this is, I find, just stop calling things object classifiers if they're not object classifiers. They're classifier between images of a data generation process. If you want them to be object classifiers, make up a data set that actually has different objects, but you can't specify that. So yeah, and then they go into some sort of adversarial examples, and I also find this to be a bit maybe not belonging here, like where they say, oh, look, here the DNNs predict guitar with high certainty. Again, it's just a discriminator, but this pattern, why not a guitar? If you had to, if you had to get one of the 1,000 classes out, why could this not be most likely a guitar? But I have a further problem with this is I kind of see this in so what you have is IID data. Let's go with their taxonomy and say IID data comes from the same generation process, and then there is OOD data. Now, I think there are a number of effects here that they try to lump together with this thing, where they just say, oh, OOD data, whenever my model doesn't work on OOD data, it has learned a shortcut, but it's very, very weird. So first of all, I would say the OOD data you can probably divide into what I would call unnatural OOD data. Let's say our task here is to build an object detector, whatever that means, for natural images. So then there's unnatural OOD data, which in here you'll find something like adversarial examples. Right? Adversarial examples are constructed, at least if you go by the interpretation of Maudry, and the adversarial examples are features, not bugs, then you'll go into the direction of adversarial examples actually constructed by combining features that don't naturally go together. So you'll get the low frequency features of a cat and add the high frequency, for example, features of a dog. So much with this lambda factor here, so high that to a DNN it looks like a dog because it has many of the features, but to a human that kind of ignores the high frequency features, it'll look like a cat. Right? But these are unnatural because the features in actual nature in the real world, they never occur in this combination. So it seems like this is a very, very, very different phenomenon from what I would call natural OOD data, where simply the features that you're seeing have never occurred in the training data set, but there is, if you go from the real world and you construct in different ways data set, there is some data set where the data actually occurs in the way that you have here. So natural OOD data is what most of the examples for now were about, like a cow on the beach. It's just because you've never seen that, because your data generation here always get cow plus grass, right? So I think these are very different. And then the last thing they also lump in here is fairness, like the fairness and bias literature, where, for example, you have a resume classifier and the resume classifier ends up being biased by gender or something like this. And again, so I kind of struggle with this, although they say not all the fairness problems come from here, but I would also like to stress that some of the fairness problem goes exactly here. It occurs because your data generation process is different from what you want. For example, if you do this hiring classifier, you have to understand what that is. What you're training is a system that will tell you how would my human dataset creators have decided on this particular application. Now, of course, there's this problem of bias amplification and so on, but it is not an infallible system. It simply tells you how the humans would have predicted. If you collect the data set in a biased way, of course, the machine will inherit that. But on the other hand, the fairness, why I don't think this really belongs in here, because in fairness, you actually have kind of an alternate world. I'll draw this in green. World prime, right? Where in this OOD and IID setting, you always assume that the world is is the world, and you want to kind of really learn a system that understands the world, where in fairness, this is your super world. So actually for the fairness literature, it doesn't really matter if in the real world let's say two groups of people are equal in some respect or not equal in the true world, right? What they care about is that they are treated equally by the system, right? So they will impose some restrictions or some condition on their model, and they don't naturally, like, this sounds bad, but it is, the mathematical formulation is such that you start with the super knowledge of two things must be equal, and then this is how you imagine your world. You think, I know the world, and then I try to learn the model such that that happens, right? Whereas over here you do something different. Now, some of it is as I said, is in the same category, but it is, I think, a different take and a different literature. So I would focus on, let's say, this part right here. On this part, and not on the adversarial examples, and also not in the fairness literature too much. All right, so yeah, you can see here, like no wonder this and this screws up an ImageNet classifier. Yeah, and even this, like, how do we know that is naturally natural? Though I can see that looks pretty natural, but still, it's probably like really specifically constructed such that the probability that someone would take this picture with a camera in the real world is 0. Cool. So they give some examples where they say, okay, shortcut learning exists in computer vision. For example, adversarial examples, you see shifting the image by a few pixels, though you have to say shifting the image very precisely by a few pixels, such that the probability of this occurring in the data generation pipeline is 0. And so on. Then they call it domain transfer. That of course is, I think that's a good example. They say natural language processing, where BERT has been found to rely on superficial keywords. For instance, it learned within a data set of natural language arguments, detecting the presence of not was sufficient to perform above chance in finding the correct line of argumentation. Again, this is like, all we can do is construct data sets. We cannot, if we could tell the model what to look at, we would just program the solution. So the solution is, there's only one solution: program better data sets, get better data sets. Or, I mean, the second solution is get better inductive biases. But if we knew the correct inductive biases, we wouldn't have the problem. Yeah, there is a, in NLP, this is very prevalent, even more than in vision, right? This fact of, hey, these spurious correlations in NLP. The models usually just learn kind of correlation between some words, and then they don't learn to understand the sentences at all, right? But this is because in NLP we have even more problems with constructing data sets that force the model to learn to understand the text. But again, I could not tell you what understanding the text means. They go in. By the way, humans do that too. Humans, in most of NLP that happens in humans do this, right? In many forms. This is simply because the cost function is not aligned with what you would want. What is the specific? Oh, well, a specific example is that news stories nowadays, right? You have a news. You say news. What do people expect? What is the intent of news? The intent of news is to inform you, maybe. But the cost, right? the cost function is clicks. So what do? You new story, and very on the top in the title, you say orange, man, bad. And then people, when you highlight this, right? So a news story, I don't know, Brad Pitt had a new baby. You just append, but orange man bad. People click on it much more. Your cost goes up. And, sorry, your clicks go up. Your cost function goes up. And so I think this happens everywhere, right? You can't even do this with humans, right? Why do you expect neural networks to do that? All right. Agent-based reinforcement learning. I find this pretty funny. Where is it? Where it learned how to play Tetris. Yeah, instead of learning how to play Tetris, an algorithm simply learned to pause the game to evade losing. Come on, it's genius, right? Like, it is objectively genius. And then, of course, fairness and algorithmic decision-making. Right, so they say understanding these shortcuts, and they touch on a lot of the things that I've touched on, including these, what I find well is, for example, this Morgan's canon for machine learning, where you say probably a machine learning system will learn the easiest feature it can, and that's oftentimes not what you want, right? So this even now amplifies things. And they also touch on this thing of anthropomorphism, where you view everything through a human lens, and that is not correct. If you look at these neural networks, they're not humans, and we should never attribute humanness to their solutions, never attribute to high-level abilities that which can be adequately explained by shortcut learning. Yes, I agree with this. Like, I agree with this paper in all the things it says, right? Except this: detecting shortcuts, making OOD generalization test a standard practice. For the reasons I specified before, I think that is counterproductive. And yeah, I think I've already said enough, right? Designing good OOD tests. You can only design good OOD tests if you know the real underlying data distribution, which you don't. And let's go 3. Yeah, again, the principle of least effort. They say, why are they learned? Because it's just easier, right? It's just easier to write a news story with just the words you know people will click on, right? Like, or these top 10 things of blah, blah, blah. Number 7 will surprise you. You don't actually have to come up with 10 relevant things. The entire title is enough to get you the clicks. So it's the least effort to solve the cost function might not align with what you want. And also the inductive biases. As I said, we are humans. We have some inductive biases. The neural networks don't have them. And we need to take this into account. But the solution is to make training data sets that take this into account. All right, they say beyond shortcut learning, this is kind of an outlook, and then a conclusion where they remind. But we're already at some 45 minutes of video, and if you're still here, like, respect, or maybe you just have this in the background and have some company during this time, I will finish with saying thank you for watching, and leave your comments. Since this is mostly opinion, I would be interested in hearing your comments on this. With that, I say bye-bye.